All right. So this is, we coined this edge native because it's like not approaching the overall problem domain from I live in the cloud and I want to go to the edge, but it's the other way. I start at the edge and I want to go and maybe adopt some of the cloud principles, hopefully all of them if we are successful. So why are we talking edge again? So back in 2010, almost everything was at the edge, right? And then the cloud appeared, and then loads of people started to swiftly move all the workloads to the cloud. And 2015, 2016, the pendulum started to swing back. It started to swing back for a variety of reasons. Some of them Tim mentioned earlier on today. Some of that is privacy and regulations, which are more fierce today than they were, say, something 2010, 2015. Data sovereignty, GDPR, certain people have to go and do stuff on-prem today just because policy tells them to. The other thing is real-time and performance aspects. You can't afford to go and send everything across the Atlantic and wait for the thing to come back if you want to go and control the robot, right? And more so these days is people discovered that the cloud is not for free. It's not for free because you have to go and transfer data there and get it back, so that transfer costs money, and even running stuff in the cloud is not for free, as we all discovered. And given that we are creating more and more workloads at the edge, largely video workloads, that we want to go and then process at the edge, we have to go and process at the edge because we can't afford to go and send everything upstream. Just consider Gare du Nord, the northern railway station in Paris. 20,000 cameras. Do you want to go and send 20,000 streams to the cloud to go get processed? Probably not. And so you want to go and process them locally. What do? You do ML at the edge or AI at the edge. And we today see more and more conversations. Like 3 years ago when I started this overall thing, AI and ML, we hardly heard about it in the context of edge. These days, 50% of all the conversation that I have these days is ML, AI at the edge. And I expect it to be 100% anytime soon, right? Really soon. So it's like ML, AI, and edge, kind of match made in heaven. So as we're doing this, as we're going back from the cloud into the edge, what we don't want to go and lose is the cloud-style development experience. So I think that's what I would call edge native. Can we go and preserve some of the good things from the cloud while we swing back all the way to the edge? So that the operational feeling is not like what I had back in 2010. What do I want, right? I want the ease of use of the edge. So we want to go and need to hide some of the edge complexities around hardware diversity, location, accessibility, multiple layers of NAT. We want to go and roll out fast, as we do on the cloud. Edge today takes weeks, sometimes months to go and roll out. And we want to go and preserve the familiar tool chain. I said edge. There's so many edges. Which edge am I really concerned about? If we follow the Linux Foundation taxonomy that they laid out a couple of years ago, right? You have centralized cloud data centers all the way on the right-hand side. You have the constrained device edge, so your sensors, your video cameras, and whatever on the very left-hand side. And then you start to go and move out. And if you look at these two things, we see these two approaches to edge reappear here as well. One way is to go and treat the edge as an extension of the cloud. I think that's the predominant principle that you see today. The edge is just yet another region for one of the cloud service providers. It is not that you're approaching the thing from, I'm completely isolated, I'm on my little domain here, and I need to go and reach out and have many of myself, my little locations, where these locations are mostly autonomous, they are really location aware, they are very heterogeneous, and, well, they're operated by people that are specialists in the art, but not an IT specialist, which is another key thing to go and consider. So don't expect that somebody could kube-cuttle to a local cluster where these guys are. So where are these guys? Who likes coffee? You had coffee. What is your favorite coffee chain?
Not Starbucks.
Yes, not Starbucks. Strike out the not. So Starbucks means I'm not sure how many, probably 30, 40,000 sites worldwide. So that's one mental model. Or like, what is your favorite burger restaurant? Same thing. Like, we're talking about things that are massively distributed to loads of little locations where we have small user-facing compute. Small user-facing compute to deliver on things like digital signage, local AI, like how many people are in my restaurant? Can I do queue optimization? Can I do drive-through optimization? Can I go and control, like what the Chick-fil-A people have done, the journey of the protein through the kitchen and make sure that the protein never ever gets older than 15 minutes and in theory is even like younger when it kind of reaches the plate. So I think that's our mental environment that we would go and address. Not really running all the way on the sensor, but one step further where you have small user-facing compute that you can shovel under some desk. So, and what we see in this space, I think, are three real transitions. Historically, if somebody said, like IoT and Edge, here is my box, and it's purpose-fit for this particular user. It's one box. Today, if you're running multiple applications there, and not just one for that one single purpose, you're typically having multiple computers of the same style, so you're starting to build clusters. And these clusters are no longer purpose-fit for a particular use because they have to go and service multiple applications. If you're serving multiple applications, you're also transitioning from loads of point solutions, like here is a solution for my smart mirror. Here's to go and count people at the entrance door, and all vertically integrated stacks into something that can be horizontal. So that I'm rolling out hardware once, I'm rolling out a platform, and then I can go and fit applications on top. Something that you do in the cloud for years, you're not doing at the edge right now, at these remote edges, right? So that we just talked about in the mental model. And yes, well, today, when we started talking to people, how long does it take to roll out an application right now, like a smart mirror application? 6 to 9 months minimum. It would be nice if you can do that automated DevOps style, right? So how does this deployment scenario look like? You might have a couple of cameras, you might have a couple of sensors that ingest information that you need to go and transform here, and you might need to have a display to go and locally show the results of that processing. Like if you see all the control screens on a shop floor, if you see like video or audio play out, or just even security camera play out. Then you have a small cluster of multi-purpose compute units. You want to go and put your apps there. And then, well, there is this hindrance between you and the world. And this hindrance might be a low bandwidth link, but this hindrance is not only low bandwidth and loads of delay, it also comes with what I'm not showing here, loads of middle boxes. Beautiful proxies, non-transparent proxies, nets, you call them out, right? Which means, like in many cases, these device edges can go and reach the cloud, but the cloud can't reach the edge. That's a problem. And you have this times n. And n might be 1,000, 2,000, 5,000, 100,000, whatever. So if we approach cloud native, like where would I start? Back in 2011, the Heroku guys gave us the 12 factors, which are pretty stable. And even after 11 years, they still apply, which is, I think, in software terms, forever. Most of these factors, like one code base, clear dependency descriptions, store config in the environment, backing services, scale by scaling the processes. So all of these things, I think, kind of apply. But we have to go and tweak things a little bit as we're moving towards the edge. And that's what I would call kind of edge native. So from a dependencies and policies perspective, we have to go and explicitly declare and isolate the dependencies and policies. Why? Because it's about location. And what happens in Germany might not be the same. What happens in Switzerland might not be the same that happens in France. Or sometimes even it's regional policies that we see quite a bit. The other thing is like backing services. Yeah, treat any backing service as an attached, potentially remote resource. So we might gonna go and have a local cluster that controls its own destiny. It might need a pull from a local repo that nobody else can go and pull from rather than yourself in that little location. Yes, it might be okay to go and pull from the cloud. You have these dependencies clearly defined, but at the same time, we have to go and adhere to that principle that, yeah, there is a notion of locality in this overall thing. From a concurrency and scale perspective, we're going to go and touch at that in great level of detail today. It's like we're no longer only scaling by processes. We need to go and scale by the sites, because these sites are kind of cookie cutter and they're no longer specific. We're no longer petting a site. We're kind of treating them as cattle. And then finally, about disposability. Processes are disposable. Workers are disposable. But in essence, also, sites will be disposable because we're scaling that element. And so we have to go and make sure that we can go and have a site trip over without any kind of problems. And finally, I think logs. I'm going to go and touch on logs as well quite dramatically, because logging is a real problem at the edge. Because logging comes with volume, and volume means you're saturating your upstream little tiny WAN link that I'm connected to. So first thing about scale, like if I'll go back to the very old model that we had, workload diversity, scale with running processes, that's the old picture if you look at the 12-factor website. Those 2 dimensions are fine. And we still run multiple processes across multiple computers. Multiple computers being like a handful of computers at that remote smart device edge. But we have to go and add another dimension, which is scale by the number of sites, because we have thousands of them. What does meaning scaling by the number of sites, or what is a site? Site is an abstract notion of location typically. So we group things into sites, and a site can be a building, but a site can also be a floor in a building, or it can be the marketing department at that particular location. So it's just an artificial grouping. It can be a cluster. It doesn't have to be a cluster. Yes, you can go and match these one-to-one, but in certain locations, it might well be that you have a factory with 20,000 devices, so one cluster might not going to go and fit it anymore. And we are deploying applications typically in this logic, like I want to go and have my application run in all the Starbucks in Zurich, or in all the Starbucks in Switzerland. And I'm going to go and deploy the application to a site. I'm not going to go and deploy the application to a particular node or a cluster or what have you. I think that's where I, as an application engineer that is responsible for controlling applications across all these locations, that's my abstraction, right? I'm not dealing with clusters. That's back to this persona that we have there. It's the practitioner that takes care of how this landscape of his applications would look like, rather than an IT engineer. Different thought model if you're coming out from the edge. And these sites are obviously conglomerates of small computers. The other thing is, like, if a site, these sites are, and I said that before, they're disposable. The nodes are disposable in the site. Yeah, we can go and fail over and have a worker node fail. Not a problem for Kubernetes. We also need to be allowing ourselves to have entire sites fail and trip over. So don't assume that these things are stateful. You always want to go and fetch the state from somewhere where it's reliable. That could be the cloud. But don't really store state locally in that thing, because the sites might entirely trip over because somebody just says, well, let's go and switch them off. Or I kind of power cycle the entire building. And the other thing is, we will never ever try to go and bug fix something locally. Never ever assume that somebody will locally kubectl to a node or a cluster that you have in one of these little sites. Why? Have you ever seen the store manager in McDonald's do kubectl? Maybe. What I've seen is when the point of sale terminal fails, so the one where you order your burger, right? What the guy does is he opens the door, he flips this power switch, and then he waits, and hopefully the thing comes back up. That's what you can expect from a debugging perspective. More? No. So if we fail, we will start over. We will trip over and we will rebootstrap the entire location if we have to. So there's only factory reset, or there might be power cycle. That's your debugging actions. And that also means if you're translating state to, or if you're pushing out state to somebody that would need to go and take an action, that's what you need to go and tell him. It's either wait, everything will be good in a minute, or power cycle, or hit this factory reset button. Nothing else. So backing services, I mentioned that already. We have this dependency declaration already in 12 factor for like the last 11 years. As we are defining these dependencies are no longer local or within reach. These can be remote. If these are remote, like the access principle becomes important because it's the site that deploys, it's the site that has the authority that can go and pull. Nobody else. There is no push operation possible from that access principle. That's also why I asked Tim the question earlier on, like, what about the services principle? Like, what would you do if clusters would need to go and reach each other? If you're really going far out to these smart device edges, they can't. So you can go and assume that you can go and reach the cloud. That's typically a given. But having the cloud reach the site, really difficult. So tunnels, don't expect them to work. It's really difficult, and we've seen this even with cloud-managed network equipment, and I work for a network vendor, right? It's a problem. It's a real problem that loads of people like start to filter out certain things in their firewalls, and even keeping pinholes open is difficult because we all remember middle boxes, NATs and whatever. There is no standard for that. If you try to go and find an RFC that standardizes middle boxes, you won't find them. There's kind of behavioral descriptions that we have by now in order to go and deal with them, but the IETF doesn't even recognize that they do exist in their various flavors. So what we can go and assume is we can push to the cloud and we can pull from the cloud. That's it. And that's also why these sites need to be as autonomous as they are, as they possibly can. Another thing on logs. Historically, this has been all about logs. And you know that like the past 10 years, we've all been transitioning from logs to metrics. Why? Because metrics are so much more descriptive. We want to go and retrieve logs on demand if we have to, because logs are like your first order of finding out where something goes wrong. But even with metrics, we found that there is too many metrics to all export at once. So how do we move from you're exporting data to you're exporting information from a particular node? And we've done a little bit of an experiment that is even implemented. And let me go and take a brief detour for this kind of light, unsupervised metrics filtering at the edge. So metrics are time series, right? And it's a really high-dimensional problem. Like you have thousands of metrics available on a compute node. If you go a little bit further and you would go and consider a router, modern routers today have easily 1 million different counters that they can go and offer to you. Which one of those matter? And you can go and plot them, and if you plot them, you get something like this, right? It's a super high-dimensional problem, and if you want to go and tell me what happens here, then be my guest. They're all different in units, in behavior, and interpretation. And you can go and start to approach that problem. Hopefully I didn't mess it up with a mic. Still good? Yes, no, maybe. I messed it up, right? Yes, no? Good? Okay. I didn't mess it up. So here's an example. We collected 5,500 counters. In this case, it was from a relatively modern router. Doesn't really matter. So that's what you see, and you see that roughly 3,500 of these counters change all the time as we plot them out. So this is the total number of counters. This is the number of counters that change. So 3,500 counters change at every single interval. Why? Because a lot of these things are counters, right? They're counting things, and they just increment or decrement or whatever. But it's worse. If you have events that we inserted here and that you didn't see on the first graph, we have an event occurring, and then 3,407 counters changed here. If nothing changed, you have 3,717 counters changed. So even the sheer number of things that change isn't really an indication. So we need to be smarter about that. So we want to go and do a filtering thing. So we need to go and start with a holistic view. and then see whether there is any change points in the data where things really start to go and transition from a state perspective of this entire system. And once we detect these change points, maybe we can even automatically describe these change points. So we are going back from like macroscopically, the system has a change point, and then can you say which of these 3,500 counters is actually descriptive for the change? Can we do this automatically? That would be great, right? Because then I can only export 5 counters and metrics, rather than I need to go and export millions of them. And luckily, when we started to explore that particular problem, the first thing is we started to go and try to understand what the structure of the data is. And what we did is we took a projection of the 5,000 counters, which is basically, well, a point in 5,000 dimensional space, and we mapped them onto a 2D projection. And we used t-stochastic neighbor embedding for that, t-SNE, which is just a visualization method. And there's something awesome happened here. As you see, it structures, it clusters. So you can see that the system is in a state, and then if an event happens, and let me map the event here, then the system seems to transition to another state, and seems to transition to another state and to another state. Why? There is research that has been done in this overall space. If you look at, say, principal component analysis of typical metrics data of computer systems or networking systems, it's inherently low dimensional. So most of the energy is around like 5, 6, 7 dimensions. That means you don't really have a problem that is 5,000 dimensions, but you have a problem that has 10, 15 dimensions in real. And that makes it digestible from an overall compute platform perspective. So we just now need to go and figure out, like, how do you detect these transitions between these individual clusters so that I can say, well, something happens here at a particular timestamp perspective. How do we do this? We can't really do this with t-SNE in an online way because t-SNE is an offline method. So you look at this whole thing holistically and then would go and compute these transitions. That's not really feasible if you have a platform that is running all the time. So what you're going to go and do there is we look at the principal angles of a time slot prior and after, always kind of 2 windows shifting apart. And then we look at the matrix, at the angles of the matrices, and if they change quite a bit, then this is an indication of a change point. I have a reference for you later on how to go and really compute that. The next problem is, once you detected such a change, what can you do, like, in order to go and then not only say something happened here, but what counters are descriptive of that change? And for that, we're loaning a method from TF-IDF, so token or term frequency and inverse document frequency. So this thing that allows you to detect keywords in a document. And we're using a similar method here, where we're saying, well, I have my general entropy for my general kind of distribution of keywords in the description of the metric, like how is the counter actually called? And then I'll see like the entropy at a particular change point, and then I'm looking for like the cross entropy between the two. And that gives me a measure for how likely this particular counter is interesting. Or like, in very simple terms, the less frequent you see something, the more important it is. And that's what we're using, and apparently it works. So when we tried this on a router, the change that happened here was a BFD, so bidirectional forwarding detection failure. That actually syncs between two devices and says, well, I'm alive, I'm alive. And these exact counters popped up with this particular method of using cross entropy between the two data sets. If you want more of that, there is much more. There's actually 2 papers that we published on this whole thing. So that was my kind of logging detour. And I'm not going to go drill further into AI and ML, trust me. So something that is kind of more to everybody's heart is probably like, let's go back to Kubernetes. And let's go back to our sites and locations and how do we control them. So if I took a very, 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 very simplistic view of Kubernetes, it's an API server where you insert state into a database, and then we have a bunch of workers that fetch state from that database and implement it. And the clusters, this one cluster is a pad. We treat them as a pad. We try to go and maintain it. It should be up and running. And the workers are cattle. Initially, I even had cattle, but now I moved to chicken because if you put a cow, it does not really work well in India. People will start to argue whether it's cattle or pets. So if we kind of apply our earlier terms around edge native, we learned that these clusters, there are so many, they are cattle for us. They can fail at any point in time. We have to go and rebootstrap them if they fail. So that means but we can go and adhere and keep the same control principle. It's this kind of clusters of cluster concept that doesn't really have to be a Kubernetes cluster. But what we need is an API, and that API is hopefully simple enough to allow this store manager person to go and roll out applications. And then you have individual sites that have one or multiple or even half a cluster that are operated like cattle, like chicken. And what you need on these sites is some operator that adheres to this communication principle with the centralized control entity. Like you can go and push your logs or metrics, hopefully metrics, not logs, because that's much more dense. And you need to go and fetch the declared state that somebody puts in. Like he would say, go and push this digital signage application to all my stores in Switzerland. And then these guys will reach out and say, yeah, well, there is new declared state for me. I need to go and fetch that particular application and install it locally. I'll realize that state locally, and I'm going to go and also pull from wherever I need to go and pull my individual containers in order to realize that state. That's it. If something would fail, and if you kind of kill this thing, it would need to go and rebootstrap itself. Yes, this comes with that these guys need to go and locally elect a leader. These guys need to go and figure out where to reach and then pull the state. And if they're offline for a couple of hours, weeks, well, they will not do anything but continue to run. Whenever they are back online, whenever they are able to go and reach the cloud again, they will scan that or re-pull that state. So I've been talking quite a bit, and I think it's time for a little bit of eye candy. So we've been playing around, and hopefully we have that available. We have a kind of experimental system internally up. A little too rough to go and completely make it available, but hopefully we have that available by later on the year. So we're experimenting with that particular concept. And let me go and show you how I would go and roll out a new site and deploy an app on that. And I'll do that with a fancy GUI. So back on this principle, we have applications, and these applications are deployed to sites. Sites are just a group of nodes. Could be one cluster, could be half a cluster, could be multiple clusters. And then we have these individual nodes, and these are small computers. Think of something that is 1,000 US or less, right? So a small box that you can shovel onto your desk, and if it fails, you just buy a new one. You don't repair it. So the best example of a small node, I'm not sure whether it's the best example, but it's a common example. And the cheapest example, it's a Raspberry Pi. So just assume this is booted up. This has a serial number so that I can go and identify it. We would go and define a site, we would add an app node to the site, and then we would go and deploy an app. So a little bit of eye candy here. We sign in, nothing interesting here. My demo environment that I have up is a demo environment with a couple of nodes, one in London, one in Paris, one in Geneva, not too far off from here, one in Budapest, and there is nothing in Cologne. So I live in Cologne, so let's go and add a site in Cologne, which is just an umbrella for the location Cologne. It's my home office, and by now you can all kind of send me postcards, snail mail, because I live in Gutenbergstraße 26 in Cologne. So if you want to go and send me paper mail, you can actually do that now. So I have my site up, and there's nothing there because it's just an empty construct. And I need to go and set, register my node that I had shown you earlier to that particular site. And then that minute, I'll actually have a location that I can also start to go and build a cluster of. Yes, this first node will become a leader. It will now kind of bootstrap, it will initialize, and after a while, it brings up an instance of a cluster and an instance of this edge operator that starts to go and check back with the control plane, and we're green now, so we can go and start to operate. So successfully started, and we're alive. And you see that I recorded that demo on the 8th of August. Next thing is we want to go and put an application, like again, in a declarative way that we're going to go and pull this down. There's a couple of things that we have here, like a little app store, like Edge AI applications or a runtime. But one thing that I want to go and show you here is digital signage for the poor. We call this event-driven display. It's just like showing you what an application for these sites could go and look like. Just an example, nothing interesting. Yes, it needs an API key so that the individual site can go and reach out to a control location. And here, like for the local device, I even set up a VNC server so that I can go and show you access to the various sites on a single screen. I put the deployment intent into the site, and now the sites will pull down that intent, and we'll realize it locally. So you see that this event-driven display thing has been installed. If I go back and look at the details, I can even see deployment example details, like nothing interesting there. So I have my application up, including on my Cologne node. If I hover over that, you'll see that there's one app deployed. Fine. More eye candy. What have I deployed? And again, like adhering to the control principles, and I'm just showing this to go and show you, like, yeah, it can be done so that it's completely decorative and we're not establishing any tunnels. So this event-driven display is just poor man's digital signage. It allows you to render content locally. And you see that quite a bit in these kind of smart edge device locations, where you need to go and show something, show local results, be it video out, be it a web page out, to go and show something. And what I'm going to go show you is rolling out content to 3 sites, Budapest, Cologne, and Roll. And for that, the first thing is I have to go and specify in control panel, like what locations, what content, and well, I'm working for Cisco, so I say go and render cisco.com. So these locations will pull the state from the central location, and then by themselves will reach out to the web, pull the content, get it down, and then render it locally. Hooray. So left-hand side is this control panel where we need to go and insert our declared state. On the right-hand side, you see VNC servers for Budapest, Roll, and Cologne. And the Cologne location, I'm going to go and switch to a video feed that I recorded with a little GoPro. So you can look over my shoulder of what I'm doing. So watch the right-hand side, and it runs my little Raspberry Pi. So next thing is I'm going to go and declare Budapest, Roll, Cologne. I want to go and push the content. There's nothing here so far. And then I'm going to go and hit bulk update, where I'm just specifying the content. In this case, it's just render cisco.com locally at all the 3 sites, instantaneously blast this out. So I'm putting declared state in, it's fetching the declared state. These 2 are actually real servers. This is a Raspberry Pi, so you see the Raspberry Pi is kind of crawling along. It takes a little while. Anyway, so that's the kind of deployment piece. That's just the tip of the iceberg. The bigger problem is, what do you do with applications that live on these edges? Because these applications also have to go and follow these principles. Plus, I have to go and abstract away to some extent that I'm running on a set of very, very small devices, a set of clusters. Because remember, I think the transition is from one purpose-built particular bull for an IoT use case to this little set of things, little tiny things, maybe a little bigger than a Raspberry Pi, probably something NVIDIA Jetson or what have you, that I'm running a multitude of different applications on. So we've looked at the fast deployment thing, so the kind of DevOps-y style. We can go and do that with our cluster orchestration system. But how about easy? And if I want to go and deploy something here, I said, I need to go and deploy this app on this set of little nodes that I have there, these multiple computers. And this app may or may not fit. So we had the discussion around data rendering, data management, all of these things are common, but the prime use case there is Edge AI. So can we simplify the Edge AI use case, the tool chain, to go and run on these edges? And let me go and spend a few cycles about that, because there is the task at hand is you have an AI model that you build. Maybe you built that with SageMaker or your favorite tool chain. And now you need to go and get it to deploy on these locations with small computers. This is a non-trivial thing, because if you train a model with SageMaker and you do transfer learning in the cloud on kind of your data with something YOLO v5, for instance, you can easily arrive at a model that is gigabytes large. Will these little nodes have gigabytes of spare memory? Answer is maybe, but maybe not. So how do we solve that? Like, let's put ourselves into the shoes of an AI developer. So I have two new models. The first one requires 100 meg, but it's still too large to fit on one of my compute nodes. And this is a real problem, by the way. We as a company, we sell cameras that have compute on box. Yes, we have compute, but do we have a load of memory up there? No, like we can put a model of up to 40 meg. That's it. And it has to be T of light. If you're 100, what do? Bummer. Or I can put my model, but the model, thanks to the beauty of my hardware, is running really slow. Actually slower than what I need. No, I'm not going to go join that call. Or should I? So I run at 2 frames a second. I want 10 frames a second or 5 frames a second. And that's a real problem, right? So if you look at monitoring or counting people at an entrance door, that's what you're typically facing. If you count quickly, and that's what an AI model with like slow frame rates would do, you count 1, 2, 3, 4, 5. If you count more frequently, you actually see that this one person is overlapping, and kind of if you're accurate enough, you can go and find the sixth person on this picture. So how do you deal with these constrained resources? Yes, we can buy bigger hardware, but that's exactly what we didn't want, right? We can go and buy dedicated hardware, but then we have dedicated hardware for my use case, and the next use case, I can go and compress the model. Everybody does that. If you're starting with a gigabyte large model, you will for sure start to optimize. You're doing things like quantization, distillation even these days, where you're trying to go and shrink the model based on the input data that you have. Or you're trying to go and cut paths through the model that are not exercised by your particular data set so that you can go and shrink it. One thing that is pretty new and fresh that we're, again, like working on, and I have 2 PhDs working on this whole thing, is if you have a big model and we have all these little computers, how about we do what you would do typically, like you would go and cut it into pieces and then distribute it. So how about we really distribute the model itself and do what we would see here? Like we have a monolithic large model, and we would split it into pieces so that the first 10 layers would run on node A, and the second 10 pieces would run on node B. Okay, so if you do this with more than 2 nodes, it's an NP-hard problem. But yes, for small sets, we can go and deal with reasonable heuristics. And if we do the splitting, it's actually more than just looking at the compute capacity of node A and node B. What we found quite a constraining thing in many cases is because these layers, their weights communicate quite a bit. What we found as a constraining thing is the network in between. So if you have Wi-Fi in between, that might be too little. So it becomes less of a concern if you have more than a gigabyte on something like YOLO v5. But otherwise, it might well be that the split is determined by the network bandwidth and not by the compute capacity of the individual nodes that is left there. Just to show you what is feasible and achievable. Left-hand side, there's colleagues actually floating into Roll office, so not too far away from here, close to Geneva. And if I run on a single node with an Onyx runtime, I reach something like 1.1 frames a second. I can be faster if I'm running the same thing on 2 nodes. Why does the number not double? Because these 2 nodes spend a fair amount of effort pushing data backwards and forward. So there is a trade-off by splitting because the network is in between, and that's kind of important. And yes, well, you can go and drive this further. The splitting doesn't have to be like that you're using the same underlying runtime on both of the nodes. You can obviously adapt if you have a node that is fit for T of light. You can go and deal better and do the splitting so that you're adapting even to the runtime, not only the compute capacity of the particular node. What can I do with this? So historically, if I had to go faster, it usually meant I had to go and compromise. I had to compromise on accuracy. So I chose a cheaper or faster model architecture. And with that, I typically reduced the accuracy. So I went faster, but my precision went down. If I do split, if I throw more hardware at the problem, I can move to higher frames per second and stay at that accuracy. And it perfectly fits this mantra of many small things at the edge. I need 3 more minutes. So final thing. We talked about inference. What about training? Training fits perfectly into this picture of edge native. So the typical thing is I want to go and train something, but I can't get access to my customer data. Because the customer wants to go and keep his data local, but we still want to go and improve the model. That's federated learning. So I have a global model. I push this global model to all the local locations. And then I'm using my private data. Think of healthcare, patient data in your dentist, doctor's office. We use this to train, and we're only going to go and upstream the changes to the model. So the deltas of the weights, we're going to go and push that up. It's less trivial than this looks because depending on what the data looks like, there could be bias that you're importing into the global model and the likes. But the communication in principle is really like you push to the cloud and you pull from the cloud. So it perfectly fits something edge native. So, well, we built a little bit of a tool chain for that to go and help federated learning in distributed environments. We call that Flame. And it fits these principles, as I said, really well. Pull the global model, push updates, and keep data private. And yeah, that's it. So in summary, we can make the edge look like the cloud if we're doing certain things where we need to go and abstract the complexities of the edge, as you've seen with AI, for instance, where we need to go and move to a model where we can indeed run small clusters of small devices at the edge, and you can still package the thing with your cloud toolchain. You can still train your models with a cloud toolchain. So most of the stuff, 95% of the things, stay the same. You can package it, you can Helmify the thing, and then you can go and deploy it with minimal deltas, a little bit of additional annotations that help you go and deploy. And that would mean, like, we can go back to that transition that I was talking about earlier on, where today you roll individual stacks 6 to 9 months manually. And they're vertically integrated. You can't share. I had a guy initially when we started talking to customers, like he said, well, I have all these little compute boxes. They're all running at 5%. Can I consolidate? No, you can't, because it's vertically integrated. And we can go and transition, right? So we can go and do our mini clouds all the way at the edges. So we can have a platform. We can have generic compute underneath. And we can then have these applications just plug in. So I think that's the mantra around edge native. And hopefully you're inspired a little bit. I wrote a blog a while ago. If you think like this is interesting, go read through it. It's pretty much the same voice track as you had right now. Well, I would really love to go and discuss with you whether these concepts really apply to your scenario, because I understand this is really far out. These are small clusters, but there are very many of these clusters, and they are not really accessible. But guess what? There is a load of use cases for these little things where we can go and transition an entire industry towards something that smells like cloud but lives at the edge. Thank you so much.